Okay, so we're talking about NMR spectroscopy, and today we'll talk about the tools that you use to identify, or the aspects of NMR spectroscopy that allow you to assign structures to molecules. So the chemical shift, which involves diamagnetic anisotropy, the word that you will impress your friends with, and spin-spin coupling, and maybe at the end we'll get to dynamics, if not next time. So as we said last time, the precession frequency of the protons in a molecule depends on the magnetic field they see, which is mostly this enormous applied magnetic field, but there are also little fields in the molecule that make a difference to give this effective field. In particular, the orbiting of electrons, the net orbiting of electrons, because they orbit both ways and mostly cancel. But a little bit of net orbiting gives rise to what's called the chemical shift, which can change the field by 12 parts per million, roughly for protons, sometimes a little more, 200 parts per million for carbon, because there are more electrons around carbon, right? But there's another effect, another magnet too. Bear in mind that the magnetic aspect of nuclei is not influenced by electric stuff, right? So that a proton, the nucleus in a molecule, is held in position in XYZ by the electron density around it. Okay, that's the bonds we talk about. But the orientation of the magnet, right, is not at all, or is rarely affected by that, right? It's affected only by magnetic things, not by electric charges. Okay, just moving electric charges that generate magnetism does it. So that it's as if the proton is on a perfect ball bearing or something. If this is the molecule and the molecule rotates, the spin keeps pointing the same way, right? It doesn't rotate with the molecule. Okay, we'll talk about that a little more in just a second. Okay, but so the things that are magnetic are the circulation of electrons, right? And nearby magnetic nuclei. They're obviously magnetic too. So if there's more than one magnetic nucleus, then you get what's called spin-spin splitting, as we'll discuss. And notice that the units are different from that. We talk about the units of spin-spin splitting in terms of hertz, that is frequency, that is energy, not parts per million, not a fractional unit, and you'll see why. So first, the chemical shift, which is due to this electron orbiting and involves diamagnetic anisotropy. Okay, we saw last time this idea that when you have higher electron density around the proton, you get more of this diamagnetic shielding and the peaks are shifted to the right. And when you have less electron density, as in the carboxylic acid, they're shifted to the left. And that made some sense. But there were things that didn't make sense, like acetylene, where you'd think that the sp hybridization of the carbon would withdraw electrons from the hydrogens and shift it downfield compared to the double bond. It shifts it upfield, right? And furthermore, as you'll see, the same thing applies to benzene. It's shifted downfield compared to other hydrogens on carbon-carbon double bonds. And the reason is this thing called diamagnetic anisotropy, which we will now discuss. So you get diamagnetism from orbiting electrons. So suppose that that red dot is the nucleus, and we're in an applied field, and there are electrons that are circulating around the nucleus, and they create, the name diamagnetism means it opposes the applied field. So they reduce the field that's seen by the nucleus, and that's the source of these splittings these shifts that we were talking about. Okay. But now we're talking here about electrons orbiting around this nucleus, the one we're looking at. There are lots of other electrons in the molecule orbiting other nuclei. What effect do they have? Okay, so suppose we're interested in the field at the red nucleus, but there's some other nucleus, the blue one, and electrons are circulating around it too. Now, what effect is that going to have on the field seen at the red nucleus? Okay. Well, we can look at the lines of force and see it has the same kind of effect, but not as strong, because it depends on 1 over r cubed. So as you move away, the effect gets smaller. That's not surprising that you can see the lines of force get further away as you move further up. Okay, so the effect is weaker from the same number of orbiting electrons on another nucleus. That's fine. But suppose that the nucleus we're studied is fixed relative to the other nuclei by bonds, by a bond like that, or other bonds. It could be connected in a complicated way to the blue nucleus. Okay? And suppose that the molecule rotates. Right? So it's not always in the same field. So we can look at it like this. Here's the, can you see this here? Okay, so here's the nucleus we're interested in, and here's the other nucleus about which things are spinning, are orbiting, right? And as we go like this, right, sometimes we're in a region where the field's pointing up, sometimes we're in a region pointing down. In fact, I have it the wrong way here because I'm going to use this same diagram for another purpose later, okay? But you can see that we're going to have to average if the molecule is tumbling rapidly to see what the influence of electrons here are when we're over here. Okay. So let's try to do the average. Okay, when it was up, when the bond was pointing up, we saw that the field pointed down. How about here when the bond is down? Which way does the field point from the blue circulation? Debbie? Look at the lines of force. Which way are they pointing? Down or up? Where the red nucleus is?
Down.
Down. Okay, so it's the same. Good. That's going to reinforce it. But suppose it's turned at 90 degrees there. Keep us going, Debbie. Now, which direction do those lines point? Up. Okay. And how about if we rotate to the other side? And how about if we're at 45, or actually a little bit less than 45 degrees there? They're pointing sort of down to the right, okay? And if we're over there, they're pointing down to the left. And if they're down here, down at the bottom, they're pointing down to the right or the left, depending on where we are. So we have to average all of these. Some of them are bigger than others. They're pointing different directions. But notice that if we average over a whole circle of rotation, then the ones that are at the top and at the bottom within the scope of those double-headed yellow arrows, those are all net down, right? Some are down very strongly, some are down very weakly, and the right and the left ones cancel one another, right, and the right to left. So it's net down at the top, net down at the bottom also. But on the sides, it's net up. Everybody with me? Now, which one's going to win? The ups or the downs? Why do you say the downs? First, there are more of them, right? And second, they can be stronger. In fact, this turns out up at the top to be the lines of force are twice as close together here as they are out here. There's a factor of 2. So clearly, the downs have it, right? So if you average around the circle, you're going to get net down. However, that's not the way you average. Can anybody see why you don't average around a circle? When I look at the effect of the fields over here on this, why don't I just average around a circle? Because the molecule is not held in a plane. It can go this way too. Okay? So we have to average over a sphere, not around a circle, right? And notice that when you average over a sphere, you get much more area around the equator than you do up at the poles going around the sphere. So now that's going to be an advantage for the ones that are pointing up, a much heavier weight in the averaging, right? And it turns out that the net average over a sphere is 0. And that's great because it means you don't have to worry about it, right? You can't get an effect from someplace, the circulation someplace else. You're only interested in the ones that are circulating about you, right? That obviously simplifies our life greatly, except for diamagnetic anisotropy, okay? So let's see what that is. So we can ignore the electrons on other atoms. Good news. Unless the amount of orbiting depends on the orientation of the molecule. And then it's not always the same orbiting for different orientations, okay? So let's just suppose that we're up there, and suppose when the molecule is oriented vertically that way, when our nucleus is above these circulating electrons, suppose there's less orbiting for some reason in that orientation. So we're going to make that pink things thinner, and that will have the effect of making the magnetic field less. The lines of force are now further apart. And that means we don't have as big a field up on top. Everybody see? So if it averaged to 0 before, it will average up now. Everybody with me? Because we've cut down on the amounts that are going up when the molecule is in this orientation. If when it's down in the other orientation you have the full complement of circulation, then the ups are going to win, okay? So and this is what's called diamagnetic anisotropy. Diamagnetic is this circulation that causes a field opposed to the applied field and is driven by the applied field, right? The reason it's there is because you put the applied field on. And if you put more applied field on, you get more of it. But in a fixed field, right, you have this diamagnetism, but it's not isotropic. Isotropic means the same in all directions. If it's different in different directions, then it doesn't cancel anymore. So diamagnetic anisotropy means that you're in trouble, that you have to consider the electrons on other nuclei as well. So let's consider that in the case of benzene. So we have these pi orbitals overlapping in benzene, and then when you put a magnetic field on in that direction, you can cause circulation of those electrons, net circulation, okay? Now that creates the field that's opposed to the applied field in the middle of the ring, but reinforcing the applied field out on where the protons are. Everybody with me on that? So it's reinforcing the applied field. However, so it's like that, but if you turn the molecule edge on, then you don't have the path anymore where they can circulate because they're driven by the big field. They circulate around the big field and now the path isn't there to go on. So it turns it off or at least reduces it when you turn the molecule that way. So this is exactly a situation of diamagnetic anisotropy where you have the effect for some orientations and not others. And now there'll be a net average field due to the circulation in these p orbitals of carbon as seen by the hydrogens, which is what you're looking at in your NMR spectroscopy. So it's a net de-shielding. The orientation shown here is the one that dominates where the field is big, where the circulation is big. It's not big when you turn it the other way, so this one wins. And this one, notice, this one reinforces the applied field at the position of the nuclei we're interested in. So that means that they get shifted downfield. So that's why in benzene, the protons are further downfield that way than you would have expected just from there being in an sp² bond, okay? Now, this then provided, once this was appreciated, NMR came along, it came along at the same time that people were interested in Huckel aromaticity, 4n+2, and it was a happy coincidence because in a molecule like this one here, which has 14 pi electrons, is that 4n+2? Right, it's 4 times 3 plus 2. So this is should be like benzene, right? 4 times 3 plus 2, and this is the NMR spectrum in the normal region of that compound. However, what comes at 0? Remember what comes at 0? That's TMS, our reference peak. And what comes at 7.2? That turns out to be the solvent, chloroform, right? So TMS and chloroform, there are no peaks for our compound, right? The reason is we have to look out of the normal range, right? So if you look for those protons, you find them way down there, further down from where benzene usually comes, which is in the 7 to 8 region, okay? And that's exactly the same region. That they're out beside the plane of this thing. The electrons are circulating around that loop when the molecule is flat like this. And it feels exactly the same kind of effect as in benzene, except more so. Okay? Now, but there are methyl groups there too. Where are they? Do we have to go still further downfield? Where are the methyl groups, right? So there's a picture of the molecule taken from an X-ray crystal structure, and you see the circulation would be around this path. Where are the methyl groups? The methyl groups are in the middle, right, where the lines of force are going the other direction. And you find them up here, right? So that's a really dramatic example of this diamagnetic anisotropy. Okay. Now, once people got this particular bit in their mouth, they started looking at a lot of other cases. For example, this molecule that we talked about, which remember had that CH2 bridge across the middle and then 10 pi electrons, 4 times 2 plus 2, right? And again, you see them shifted downfield when they're outside and upfield when they're inside, okay? Now, they're not shifted as far. Why not shifted as far? There's not as much ring current. There are not as many electrons, but the other reason is that that was distorted, so the overlap isn't as good and you don't get as much circulation. Right? But still, you can see that it is benzene-like. It is, in this context, aromatic because the CH2 is shifted up above TMS, very unusual. Okay. Now, that's 14 pi electrons. Suppose you treat it with potassium. Potassium easily gives up electrons. It reduces the compound. In fact, you can put 2 electrons into it. And for this purpose, we're going to condense the scale. Same spectrum, but I just squeezed the scale in for reasons that will be obvious. Okay, so they're the sort of super aromatic hydrogens shifted downfield to about 9 parts per million, and the ones on the inside shifted way up. But if you put 2 more electrons in and make the dianion like that, now it's not aromatic anymore. It's 4N instead of 4N plus 2. And look at its NMR spectrum. They exactly shift, right? So aromatic goes one way, Huckel, anti-aromatic goes the other way, right? So there were lots and lots of examples done like this during the 1960s and early 70s. Okay, so the CH3 signals shift downfield by 26 parts per million, despite adding, remember there are more electrons now. We put 2 more electrons into the system. They should shield it, but in fact it's de-shielded by 26 parts per million. Really dramatic. Okay, so it's an anti-aromatic dianion. Now, how about acetylene, right? Now, acetylene has these p orbitals. We're written at vertical here. They're 2 p orbitals. And remember about when we talked about what the electrons look like if you have p orbitals equally occupied? If you have 3 p orbitals, each with 2 electrons in it, and look at the total electron density, what does it look like? It's a sphere, right? It's not lumpy. And 2 give a cylinder, right? So this thing has a cylinder around the carbon-carbon triple bond, right? So there's a path in which electrons can circulate, okay? So we get this diamagnetic current when we put a field on that and get these fields. How is this different from the case in aromaticity, do you see? When it was benzene, it could circulate when the molecule was flat, right? And the hydrogens were out here. Now it circulates when the molecule is oriented this way and the hydrogens are above the middle. So the lines of force go exactly the opposite direction. But as in benzene, when you turn the molecule, you don't have the path for circulation. So it's diamagnetically anisotropic. It goes one way and not the other. This is the way that wins, and the nuclei of acetylene lie above the orbiting path where there is ring current. So the applied field is diminished and the signal shifts upfield rather than downfield. So that's why when you made it SP rather than SP squared, it didn't go downfield because of the electronegativity. It went upfield because of diamagnetic anisotropy, and it's just the opposite of what you see in benzene, where the protons are beside the circulating path rather than on its axis. But here's a warning. This is a handy picture and has been taught for 50 years now, I guess, close to. But it might be nonsense. And Professor Weiberg has done calculations and observations that show that it doesn't work for C13. Whether it works for protons, I'm not sure. But at any rate, it's a really handy picture to remember who shifts which direction. And it has sort of the ring of truth about it, but it might not be supported by really careful calculations of the kind Professor Weiberg does. Okay, so that's the idea of diamagnetic anisotropy and what gives rise to chemical shifts, these things we talk about. Pulling electrons away, mostly it's the electrons on the nucleus in question that are important. And as you pull the electrons away, you get a shift downfield, right? Pardon me, downfield. Downfield's that direction for you. Okay, good. Okay, but in special circumstances, you have this diamagnetic anisotropy, and then you have to think about it in the terms we just talked about. But there's also the local fields that are due to other nuclei, and this is called spin-spin splitting. For example, this is taken, and again, I will recommend to you this Chem 220 website, which has NMR problems. They give you a spectrum and say, what is it? And then the nice thing is they show a spectrum like this. They allow you to go in and look in detail at the peaks and see what their integrals are, and also gives a detailed explanation, so there's an answer key. So that's a handy place to go. But this is the first problem in that set. Now you can see there are three kinds of protons in this. It turns out, I'll give you the answer first, that it's ethyl acetate, okay? So there'll be two groups of 3 protons and one group of 2 protons. So obviously these are the 3 and that's the 2, okay? But let's zoom in as this program allows you to do, as that website allows you to do. And when you look at that triplet, you see that when you look at that peak, you see it's in fact 3 peaks, and they're in the ratio 1 to 2 to 1 in their intensity. Now, why is that? Those are the CH3 groups of the ethyl group, CH3 protons of the methyl group, right? But adjacent to it, there are 2 other protons in the vicinity, right? And you can have those oriented, each of those can be oriented either with or against the field. So there are 2 of them, each can be with or against the field. So there are 4 different ways to do it, okay? 2 to the 2. Okay, so they're different molecules which have different orientations of next door protons, okay, of those protons. Now let's think about those. They could both be down, they could both be against the field, and then we get this peak, okay? Or they could both be with the field, and then we get this peak, okay? So that you have, when you think you have just one kind of molecule there, in fact you have what you might call, nobody calls them that I think, spin isomers, right? They differ only in how these neighboring protons have their spin oriented, but they're different molecules in there, okay? So but they are so similar in energy, the magnetic interaction of the protons with the field is so small in energy that the Boltzmann constant is 1, at equal amounts of the 2. I mean, there's a tiny, tiny difference, but not that you could measure by the intensity of the lines. So they're equally abundant, so the yellow peak is just as big as the blue peak, or green, okay? Now, what's that? That's when one of them is up and the other is down. And it's just as likely as the others, so it's 1 to 1 to 1. But you can also have one down and the other up, right? The opposite direction. And so that's why it's 1 to 2 to 1, because they're all 4 of those are equally likely, and 2 of them come in the middle where they cancel each other in their effect. Okay, so that's a triplet. Now, how about this thing here? That's a quartet. And we can figure out how that works too. That's the CH2s. Why are they shifted downfield? Why did they come farther to the left from where the methyl group was? The chemical shift, Derek?
Oxygen.
Because the oxygen's withdrawing electrons. Okay, so they're shifted down there. It integrates for 2. That's how many protons are being involved. So it's that CH2 group. But it's a quartet. Why? Well, let's look at the neighbor. Now there are 3 hydrogens on the next door carbon. So there are going to be 8 different spin isomers that differ in the spins then of the adjacent hydrogen nuclei. So let's think about it. They're the ones where they all oppose the field, they'll be up at the right. The one where they're all with the field, that'll be at the left. And then you can have 1 down, or 2 down, or a second one down, or a third one down. But they're all the same, right? All have 1 down, so they come to that peak, and then there's one of them up, a different one up, a different one up. So it's 1 to 3 to 3 to 1. Okay, so if we have 3 neighbors, we get 1 to 3 to 3 to 1. If we have 2 neighbors, we get 1 to 2 to 1. What if you have only 1 neighbor? What pattern should you see? Poyi? If you had just 1 neighboring proton and you're looking at this one here, what will the signal of this one you're looking at look like? Right, there'll be a peak like one. Some molecules will be like that, others will be like that. It'll be 1 to 1. Okay? So if it's just 1, it'll be 1 to 1. Now, what if it's 4? Anybody know what that one's going to be? Yeah. 1, 4, 6, 4, 1. How did you get that? Right, it's Pascal's triangle, the binomial coefficients. So it looks like we can do this for anything, right? We're in good shape. Okay, now how big is this splitting? It's measured in energy units, in hertz, and that's called J, and they're equal. You expect those to be equal because both of them involve the same change in the neighbor, right? Flipping 1 proton. Okay, and at the same time, those are all the same too. But this is exactly what you should say, because the influence of this magnet on this magnet has got to be the same as the influence of this magnet on this magnet, if they're the same kind of magnet, all protons, right? So that's great. And notice, it won't depend on how big the magnetic field is, because this is just the interaction between 2 magnets which have fixed magnitudes. It was different for the orbiting, because the orbiting was created by the magnetic field. When you had more magnetic field, you got more orbiting, right? So the chemical shift is measured in fractional units. What fraction of the big field does it shift at? Some parts per million. But this is measured in hertz, in energy, because it doesn't depend on the applied field. So it's independent of B0 versus the chemical shift, which, as we know, does depend on B0. The orbiting is driven by B0. Okay, now let's look at another one. This is ethanol, a spectrum measured over the break by Phil for us. Okay, now, so we got OH, CH2, and CH3. Let's see if we can figure out all these peaks. Which one is that furthest to the right? Which of the protons in ethanol is that peak that's furthest to the right, which turns out to be a triplet? What?
It's on the methyl.
It's on the methyl group because the other ones have oxygen withdrawing. So it's it has the highest chemical shift, or the lowest number of chemical shift, the least shifted down from 0, right? And it's a triplet. Does that make sense to you that it should be 3 lines? Kate, what do you say? Why? No, it's 3 protons, right? But the signal is not a single peak 3 times as big as the others. It's 3 peaks, 1 to 2 to 1. What causes that splitting? You remember? It's not chemical shift. It's called spin-spin splitting. What's the other spin that's splitting your signal? It's the protons on the adjacent carbon. And there are 2 of them, and you can orient it in 2 to the 2 ways, 4 ways. 1, bum, bum. Okay, that's what we just talked about. So it's a triplet, that's what you expect. Okay, so that's the splitting of the CH3 by the CH2 protons. Okay, now let's look down at the other end. And incidentally, the chemical shift positions as measured on the spectrometer are that, but actually we should measure it not in parts per million, where the difference is 0.018 parts per million. We should measure it in hertz. So the hertz units are 7.2 hertz. We multiply by the frequency of the spectrometer, which it says here is 400 megahertz. Okay, so it's 7.2 hertz. Okay, now we look down there and we see a triplet. What's that due to? Alex? Yeah, why? Why is it the OH? So it's got two neighbors, right? Okay, so and it's shifted all the way downfield because the oxygen electron withdrawing, it would appear. Okay, so that's the CH2 splitting the other direction. Now let's compare those two. They're not the same size. The interaction between the OH and the CH2 is smaller than the interaction between the CH3 and the CH2, right? That one is 5.1 hertz. Okay, now what's this thing here? What's that due to? Matt?
This protons on the CH2.
So that's the CH2, and what's it split by?
The H on the OH, and the H is
okay.
the CH2.
So how many H's altogether?
4.
And what do you expect the intensity to be? 14641. So let's blow it up. Okay, is it a 14641 quintet? Not quite. Now, what is going on? Notice that those two interactions are not the same, right? One is 7.2 hertz and the other is 5.1. So if we look at those, there we see a quartet. That's split by how many? That's split by 3. That's the CH3 splitting. But in fact, they're two quartets, right? So that's the smaller splitting due to the OH. Now, had they been the same, then the separation of the three and the separation of the two quartets would have been, would have been, instead of being like this, it would be like this. And then it would be 14641. Right? But it doesn't look like that. It's actually what we call a doublet of quartets, or a quartet of doublets. Okay, so that's a little bit different. Okay, now there's some other tiny peaks here. What's this one due to? Any thoughts? What?
Water.
Good idea. Could be water, but it's not. The solvent is DMSO, D6. But unless you would spend an absolute fortune, you have some DMSO D5 in there that has one proton, right? So those few molecules of the solvent that have hydrogen on them look like that, right? So you see a signal from that. Okay, that's fine. And that's what the signal looks like. Now, there are no other hydrogens in there. What's causing spin-spin splitting? Deuterium is also magnetic. It's not a very strong magnet, so it doesn't have a very big splitting. These splittings are very small, right? And furthermore, not only is it a weaker magnet than a proton, but so that it's only 1.8 hertz, right? It can be oriented 3 ways in the field. Remember, a proton can be with or against, but a deuterium can be with, against, or across. So now there are 3 ways of putting it. So if you have 2 of them with 3 ways, it turns out what you get instead is a 1, 2, 3, 2, 1 quintet. And you can work that out for yourself. If a single one splits at 1 to 1 to 1, because there are 3 orientations, right? What do 2 do? So you can work that out. If you figure that out, then you'll understand the math we've been doing here. Okay, now here's another peak. Matt, what's this peak? Why did I ask you?
Is that water?
That's water.
Yeah.
Okay, good. Okay, but look over here.
Just ignore this.
What are those? Blow it up. This bit here, these little ones, are due to an artifact of the instrument. Don't worry about those. But these are real, here and there. So they both look, they're triplets, right? Like what's in the middle of them is a triplet, right? And there's a 7.2 hertz splitting, which is exactly what you had here, right? So it looks like it's being split by the CH2 next door. That's this splitting here. We're looking at something that has to do with this CH3. It's being split by that, but there's something else that's splitting it. What else could be splitting it? there's another magnetic nucleus. It can't be this H out here because that's so far away it would have a minuscule effect. This is an enormous effect, this doublet splitting. Any ideas? It's sort of related to this one, actually. There's another nucleus there that's magnetic, but only 1% of the time. These are only 0.5% as big as this is, right? So the total of this and this is just 1%. There's 1% of some other magnetic nucleus in there. Carbon. It's carbon-13, right? And that has an enormous interaction with the protons, 125 hertz. It's much closer to the protons. Okay, that's 1.1% of carbon in natural abundance. But notice one other thing that we're going to address later, probably we won't get to it today, which is that these are slightly asymmetric. This one's just slightly bigger than that one, right? And the green ones here are slightly bigger than the pink ones, right? And this one is slightly bigger than that one. And we'll get to that too. So we've looked at this in pretty much detail. Now, what determines the strength of the spin-spin splitting, how many hertz it's going to be? And so we're going to talk about isotropic J coupling between protons. And it's not a through-space magnetic interaction. It's mediated by bonding electrons. Because that's what this was actually made for. Here are the lines of force created by this nucleus, and we're looking at this one. So it can be like this, or it can be like that, okay? So we get a doublet of when we're looking at this proton over here, because this one can be either this way or this way. But if we follow its lines of force, they can either oppose the applied field, or they can help the applied field. And what do we get if the molecule is tumbling in three-dimensional space for the average of that? Zero, because now you're not going to get diamagnetic anisotropy, because this magnet has nothing to do with the circulation of electrons and where the paths are. It's just the nucleus itself. And they're on perfect ball bearings, right? So there's no special stuff going on. So it'll absolutely cancel to zero. But then how in the world do we get interaction between the two? How do we get splitting if the through-space interaction of magnets won't do the trick? Okay, it goes through bonds. And let's look at this. So let's look at the magnitude of some of these coupling constants, as they're called, J. Okay, so for adjacent positions in benzene, it's 6 to 8 hertz. For next adjacent positions, it's 1 to 3 hertz. And for remote positions, it's 0 to 1 hertz. So what does it look like it depends on? Any thoughts?
The position of the H's.
Yeah, it depends on position, obviously, but in what way?
The closer they are,
The closer they are, the bigger the interaction. Can I see the hands of those who are surprised? Okay. Okay, now let's look at these. That's 1.85. This is 2.38. That's 3.07 angstroms. And here are their coupling constants. What do you think of your theory, Derek?
It's not holding up right here.
What?
It's not holding up right here.
It's exactly wrong. The closest ones have the smallest splitting, and the farthest ones have the biggest splitting. But we know that it shouldn't be distance, because we've just seen that it averages to zero. So it must be something else. Okay, it's not spatial proximity. The through-space interaction of dipoles averages to zero on tumbling. Okay, now let's look at ethane here, and look at those two protons, top right and bottom left, and look at this particular molecular orbital, which turns out to be HOMO -3. There are lots of others we could look at, but this one is good to look at for reasons you'll see. Now, when there are two electrons that are going to be in this orbital, right? And when one of them is on this nucleus, the one, let's say the electron, remember it's magnet too, when it's pointing up, there's going to be, in that orbital, there's going to be one electron pointing up, one electron pointing down. Okay? So suppose the up one happens to be here. Then The down one can't be up there. Only the down one can only be over here. That is, only the down electron is available to be here. It can't be the blue one when the blue one is up there. Okay? So the electrons provide a way to communicate between the nuclei. Like, suppose that this electron likes to interact with that nucleus when that nucleus is up, let's say. Okay?